Hello, I am Krishna Narasimhan and welcome to my PhD defense titled Combining User Interaction and Automation to Evolve Source Code. Thanks a lot for being here. So let me begin. Software evolution is inevitable. If any of you have a device or have been using a service that has software running in the background for any reasonable amount of time, you must have watched it change, sometimes leaps and bounds beyond your imagination. So how does this evolving software manifest itself? From the user perspective, he gets access to cool new features and he also gets access to better performance and things like that. But for every such cool new feature or improved performance, there is a bunch of developers sitting in the background, sometimes in front of a lot of multiple screens and making changes to the program source code. Focus of this thesis will be concerned with the kind of changes that the developer makes to the source code in order to evolve the software. So why is this evolution of source code challenging at all? For starters, source code these days are no longer just a couple of lines of code that print out hello world. Any non-trivial piece of software has sometimes millions, if not hundreds of millions of lines of code. And it's of course imaginable that maintenance at such scales of the source code is really hard. And we live in a day and age where it's not just professional programmers who are trained to maintain source code that actually write source code. Physicists write code, bankers write code, biologists write code, and they maintain code, they evolve source code. And of course, they shouldn't be worrying about all the challenges of source code evolution when they're maintaining their source code. So first let's begin by seeing what a developer actually does when he's evolving his source code. Either he's writing new code or he's rewriting existing code. And research has suggested that when developers write code, much of new code is, not much, but I mean, a large chunk of new code is very similar to existing code. And this leads to a scenario where the developer is reusing parts of the existing code to develop his new code. And the research community has given the umbrella term source code reuse to describe this scenario. When rewriting old code, what the programmer is doing is basically transforming program from one form into another. And the research community has given the umbrella term source code transformation in order to describe the scenario. So, the focus of this research was to delve into some of the unexplored maintenance tasks that come out of these two scenarios, source code reuse and source code transformation. And of course, when performing research, we have to establish why the research that we're performing is tackling a significant problem, especially when you're talking about developer preference. The research also came up with approaches which are automatic but guided by user interaction to help the developers accomplish these challenges, to help them with source code reuse and transformation. And since we are talking about developer preference, we also need to evaluate for their feasibility and usability. So, this talk will be split into two parts. The first part will look at a research problem that arises out of source code reuse and how to help developers tackle that problem. And similarly, the part two will be concerned with a similar scenario with source code transformation. So let's begin with source code reuse. How do developers actually reuse source code? There are two primary ways that developers employ to reuse source code. One is copy, paste, modify. Copy, paste, modify is simple. Let's look at a scenario where the developer who wants to implement cost function 2 has only cost function 1 in the access. So when he's implementing cost function 2, he first identifies cost function 1 as a similar functionality and he says, okay, let me just copy it, paste it, and make changes to this line of code, the last line of code, which will make me calculate cost function 2. And that's one way of reusing source code, which is copy, paste, and modify. The other way is to actually abstract code. Abstraction actually begins by identifying the code similar to the existing code, but instead of copying and pasting, the developer thinks to himself, hey, I don't want to create a duplicate copy of the existing code because that will only bloat up the source code. Let me just go ahead and create a super function or a super method which will be able to do both the functionalities of the existing one and the new one that I wanted to do. And in this example, what he could do is he could simply create an if conditional branch, and he could use that if to branch between one or the other cost functions and retain the common code as it is. And he will use a Boolean flag to switch between one or the other functionalities. So now that we've seen two primary methods on how developers reuse functionalities, reuse source code, we want to understand the pros and cons of each and to see if there is a research problem here at all. So what we did was, if you're talking about developer preference, you have to make developers sit in one place and actually develop code. So we recreated scenarios where programmers could actually reuse code. We put them in a room and we asked one group of developers to reuse functionalities using copy paste, another group to reuse functionalities using abstraction, and the results were kind of obvious. People who used copy paste did their tasks much quicker. So does it mean, but we want to understand why there is abstraction at all. So after they completed their tasks, we asked them to imagine a scenario where they are not the ones developing it. Let's say they were the bosses and they were just maintaining the code, and they could order their employees to develop whichever code they wanted so that they can maintain it. And it turned out that for majority of the tasks, the developers said they would have preferred to maintain the abstracted version of the code. And now this leads to a surprising source code reuse discrepancy, which is that copy paste modify seems to be easier. Developers seem to find one method easier to use when they are actually developing code, but they seem to prefer another version, abstraction, when they're actually maintaining the code. So our proposed solution is the best of both worlds. We say that developers should go ahead and use the method that they like to use when developing code, which is to use copy, paste, and modify. And then they invoke a novel merging approach that is proposed by us, which takes in these copy pasted code and produces an abstracted version of the code. So for the rest of part one, we will have a look at how this novel merging approach works. On the high level, we will look at a couple of examples of real code being merged using our approach, and we'll see how we evaluated our approach. So the novel merging algorithm on the high level begins with what is called a near clone method. A near clone methods are a group of methods that arise out of this copy paste modify practice. Basically, when a developer is copying a method, pasting it, and modifying it, what he's doing is he's creating a near clone of the existing method. And this goes on, and you have what is called a near clone method group. And our merging algorithm takes as input these near clone method groups. And then the first step it does is it detects the merge points. Basically, detecting the merge point is a step where the algorithm says, these are the common bits of code, these are the different bits of code, and these are the places where the different bits of code can be merged. And the algorithm does this using the abstract syntax tree of the code. It extracts the abstract syntax tree and it identifies these merge points. But once the merge points are detected, till detecting the merge point, the algorithm is very generic and it's oblivious of what language it's using. But in order to resolve these merge points, we have to use programming language constructs. For example, we already saw one such merge point resolution, which was to actually use an if conditional branch in order to merge two statements. So to resolve merge points, we needed to design a tool that works on a particular programming language. And for our purpose, we chose C++. And in order to understand what are the ways of resolving these merge points, we had to conduct further research. So what we did was we looked at popular open source repositories from Google, Facebook, and Intel. And we used these repositories because we wanted our insights to come from actual industry code and not just toy programs that were built as part of mini projects. And we studied a lot of these clone groups and we arrived at the top three kind of differences. And the top three kind of differences that turned out were statements, constants, and types. We already saw how we could resolve statements using conditional branch. We also implemented our tool to be able to resolve statement level differences using switch statements. And we came up with a couple of ways to resolve constants differences, and we came up because we are using C++, we could resolve type level differences using template parameters. Of course, there are many other ways each of these differences could be resolved. But for implementing a prototype tool to evaluate our research hypothesis, we started with a couple of methods, one or two methods for each of these kind of differences. Now let's look at a couple of examples of real code which was merged using our approach. So The first example is from Facebook's RocketDB repository. RocketDB is basically Facebook's internal key value pair storage system. And this is a near clone method pair, and these methods are much bigger than they actually appear here. I had to squeeze them out and comment out a lot of the common code. But the thing that is important to observe here is that the only difference between these two functions is actually the statement where the value of s is set. And our tool began with this near clone methods and produced an abstracted version of the code which uses a switch statement to branch between one or the other statements. And the bodies of this near clone methods were replaced with just one line, and that one line was basically a call to this abstracted function where the corresponding basically function identifiers were set. If it is 1, this abstracted function would branch into this statement. If it is 2, the abstracted function would branch into the other statement. Let's look at another example of an actual merge performed by a tool. So this is a function pair from Oracle's NodeDB repository, and actually this group had more than 2 functions. They had four functions, all differing by just one constant. I had to squeeze in only 2 of them for sake of readability of the slides. And the way our tool resolved it was it created an abstracted functionality where the constant was resolved using an extra functional parameter, and the functional parameter has a type string after performing some type analysis, and then basically the parameter was replaced the actual constants in the abstracted function, and basically the bodies of these functions were replaced by calls to the abstracted functionality as before, and the constants were actually passed as the parameters. So these are a couple of examples of how our merging approach works. Now that we've seen a desired problem in source code reuse, which is to be able to move from copy pasted code to abstracted code, and we've seen a high level view of the algorithm, and we've also seen actual applications of the tool. Let's see how we actually evaluated it. Because we're talking about developer preference, we wanted to understand if developers actually like to use the code produced by our tool. For this, what we did was we submitted what is called a pull request. A pull request is basically pulling open source repositories and making changes to those repositories and requesting the developers to replace their code with the request that we submit. So what we did was we took open source repositories, of course, ranging from Facebook to Google and actual industry open source repositories, and we detected detected clone groups in them. We merged them using our approach, and we submitted pull requests. And majority of the pull requests were accepted. And what is more interesting is that our approach we had built 2 versions of the tool. The first version of the tool worked with only method pairs and could only merge one merge point at one point of time. But we upgraded our tool to be able to handle multiple methods and also merge multiple merge points at the same time. And more than 90% of the results produced by that version of the tools were accepted. And this is the kind of interaction that we had with the developers as part of our research. And what basically after we submit a merged version, we would get feedback saying, hey, we like the merge we produced. So could you, and we will perform some tidy up, and we'll actually merge it as part of our tool. And then the pull request will be complete when the merge is done. So let's move on into the part 2, which is source code transformation. As many of you know, source code transformation is an area of research that is fairly mature, and a lot of problems have been tackled before. So if we have to do something here, we have to do it right. So we wanted to identify some problem which was really significant and not explored before. So before that, we needed to understand what are the kind of existing tools that support source code transformation. The tools that many of you have used source code transformation tools, but haven't just known that it is source code transformation. One of them is the refactoring tools that all of you have used as part of your development environments like Eclipse or NetBeans. So consider this refactoring rename variable. Basically, you're transforming your code from the form where the name of this variable is beaninfo into a form where the name of this variable is, let's say, beaninfo2. The advantage of such refactorings is that refactorings happen selectively. So basically only this variable is renamed and all the dependencies of this variable are renamed, not everything else. So refactoring tools provide transformations which are selective based on the dependence of the code that you just transformed. But the problem is refactoring comes with a limited vocabulary. For example, refactorings are, you can perform rename variables, you can perform extract methods, you can only talk to refactoring tools based on the vocabulary that is provided to you. You can't customize refactoring tools, although they are very powerful program transformations. So an alternative to that is transformation languages. Transformation languages allow you to express sophisticated transformations, like saying, hey, I want to transform my code, which has a statement which looks something like this, into an expression that looks something like that. And popular transformation languages are Stratego and Coccinelle. The advantage, of course, as we've seen, is that they're customizable, but the disadvantage is that it is difficult to express the kind of selective data-dependent transformations that refactoring tools allow us to do. So let's look at a particular transformation problem that seems to require both the cons of transformation languages and the refactoring tools. Data migration. Basically, data migration is a problem of transforming in code where you transform only one data from one representation into another. For example, here in this function, the developer may want to transform the value of p from the int representation into what is an mpzt representation. mpzt is basically a type that comes from the GNU's API, which allows you to represent big integers. So basically, this is a big integer here. And so for such a transformation, one, you want the dependency tracking of refactoring tools, because you don't want to transform all of the ints into big ints. You only want to transform p. You don't want to transform n, or you don't want to transform I. And so you want the dependency tracking of refactoring tools. At the same time, these are not simple rename variable refactoring source, or you need customizability. You want to transform the statement that looks like this into a couple of statements. You want to transform this multiplication assignment into a function call here. So basically, you have a problem of transformation here where you need the dependency tracking of refactoring tools and also the customizability of transformation languages. So our solution is data representation migration framework. Basically, data representation or DMF has two parts inspired by the two popular transformation language approaches. One is a transformation language where you specify rules to pattern match and transform code, which gives you the customizability. For example, this rule here transforms a statement that looks like this into a couple of statements that looks like this. And this rule here transforms a multiplication assignment expression, which looks like a equal to b star c, into a function call expression, which looks like mpz mul ui abc. And it also has another part which is inspired by the refactoring tools dependency tracking, which is the transformation engine. The engine basically selectively, it works implicitly. You don't have to invoke you basically select a piece of code and you say, hey, I want to apply this rules on the code that is dependent on this. And the transformation engine would go ahead, detect the dependencies and apply these rules on only the dependencies of this code that you selected. So how did we evaluate DMF? The first thing is we wanted to understand if the problem we are tackling is actually a significant one. We don't want to, for the first source code reuse bit, the significance was established using user studies, and actually the problem was already there in research literature. For data migration, we evaluated it first by building our tool and actually performing transformations using our tool. And we transformed a code from array of struct to a struct of array, which showed better performance. We transformed a code from int to big int, which showed better precision. And we transformed a code from scalar to vector, which showed improved runtime. So now this doesn't establish anything about our tool, but it establishes that the problem our tool is tackling, our research is tackling, is a significant one. So as I already described before, our approach had two parts. One is the language and the other is the transformation engine. In order to evaluate the language, we wanted to test if the specifications written using our language is broader than just one example. So we used the int to begin specifications and applied it to 11 other algorithms, and we tested them, and it seemed to produce the desired results. And in order to test the engine, we wanted to see if the engine terminates within a reasonable amount of time. So we ran our approach on a fairly large code spanning 3,700 lines of code with a lot of dependencies, and the termination happened within 2 minutes. So now that we've seen a couple of significant research problems and how we tackled it, let's look at the contributions that we made to the scientific community. With the source code reuse bit, we submitted a couple of papers to top-tier software engineering conference. One of them was our distinguished paper in the research track of the conference. And also prototype version of the tool is available in the Eclipse marketplace, and it can be installed and tested out on codes, C and C++ codes. And for the source code transformation problem, we got a paper accepted in PEPM, and vision of this paper was also peer reviewed and accepted a couple of years ago in eCoop 2015's doctoral symposium. And the source code of this is publicly available in GitHub. So, in conclusion, we understood that manual source code evolution is hard. We researched a few underexplored problems that are very significant when it comes to source code evolution. And we designed automation approaches which were guided by developer interaction. And we implemented prototype tools to evaluate our design, and we evaluated for the usability and feasibility of our design using these prototype tools and actual interaction with developers. Thank you.